Okay. This. All right. So welcome everyone to the security session at the IEEE Virtual Reality Conference 2022. My name is Babu. I'm from Clemson University. And so we have 6 presentations today. And our first presentation is by Florian Mathis. The title of his paper is Virtual Reality Observations Using Virtual Reality to Augmented Lab-Based Shoulder Surfing Research. Florian, please present your
I'm here.
paper.
All right. Thanks a lot for the introduction. Good morning, good afternoon, and good evening, everyone. My name is Florian, and it is my great pleasure to present our IEEE VR paper, VR Observations Using VR to Augment Lab-Based Shoulder Surfing Research. So let me first introduce what we mean with shoulder surfing. Shoulder surfing is the act of observing other people's information without their consent. And in this example, someone looks over someone else's shoulder to access their PIN while they interact with an ATM. Now, the problem here is that researching such sensitive and private contexts in the wild is often infeasible due to ethical and legal constraints. As a result, a common method is to invite user study participants to the lab to then let them watch pre-recorded lab videos. And these videos then show a user who authenticates using a novel authentication mechanism. And in this case, on the bottom left, you can see that the user is using midair gestures to authenticate. And I think it's quite clear that watching 2D videos on a PC does not really represent how shoulder surfing actually happens in reality. And more importantly, it does not enable researchers to get insights into attackers' observation behavior. And getting those insights is particularly interesting and important because human-centered security researchers need to understand how attackers behave to incorporate these findings into the design and implementation of usable, secure, and privacy-preserving systems. And this is where VR, combined with traditional user-centered security research, can contribute to more realistic shoulder surfing research. From previous work, we know that VR-based 2D videos form a valid baseline to assess the system's security against such observations. So for example, if a researcher or a practitioner wants to evaluate the security of a novel authentication system for mobile devices, they can pre-record videos that show an avatar authenticating and then let participants watch those on a PC to guess the entered PIN. Building on these findings in this work, we make use of VR's characteristics to provide attackers with the opportunity to position themselves in the authentication environment through traditional keyboard and mouse input, defined as non-immersive VR or desktop VR. Furthermore, we look into immersive VR to allow participants to physically move around in the authentication environment with the aim to provide them with a closer to reality shoulder surfing experience. This means that we compare in this work the impact of 2D videos, non-immersive VR, and immersive VR on the evaluation of security systems and their impact on user study participants' perceived shoulder surfing realism. We conducted a within subject experiment with 18 participants to evaluate the different observation methods. We also aim to get insights into participants' performance when observing authentications in different scenarios. We studied ATM authentication, phone PIN authentication, and phone pattern authentication. We then compare participants' sense of presence and perceived workload when using the different observation methods. And we also conducted semi-structured interviews at the end of the study to better understand participants' shoulder surfing experience when using the different observation methods and to pinpoint differences to their prior experiences in the wild. And when we take observations on smartphone PIN authentications as an example, we noticed that immersive VR observations resulted in participants successfully observing more PIN entries than when using non-immersive 3D observations or 2D observations. 3D observations negatively impacted participants' observation performance compared to 2D video observations. This means that at the point where researchers' aim is to assess a system's security, non-immersive VR observations might not be suitable, as the corresponding results may overestimate the system's security. There was no significant difference between 2D video observations and VR observations, which suggests that immersive VR observations are suitable for assessing a system's security. When comparing participants' sense of presence between the observation methods, we noticed that VR observations led to a higher sense of being part of the shoulder surfing scenario, to a higher spatial presence, and to a greater feeling of involvement and experienced realism than watching authentications on a desktop PC. While this is an expected finding, with the benefits of immersive VR being well known to the VR community, the advantages of VR over traditional 2D videos are particularly interesting for shoulder surfing research, because our findings imply that previous lab-based shoulder surfing studies were not necessarily capable of providing participants with a close to reality shoulder surfing experience, therefore often impacting the ecological validity of user-centered studies in the lab. And what is particularly interesting from a human-centered security perspective is that non-immersive and immersive VR enable researchers to log observations and actually the positions of attackers, and provide researchers with a glimpse into attackers' observation behavior. For example, some participants exploited non-immersive VR's unique affordances to perform observations from positions and angles that would otherwise require a drone equipped with a camera, for example, as you can see in the top right image. Some others combined the observation with another task, such as pretending to tie their shoes, as you can see in the bottom right here. And receiving insights into attackers' potential observation behavior is important for the design and implementation of such security systems when we talk about authentication systems. In summary, our findings show that 2D videos are sufficient when the aim is to evaluate a system's resilience against observations, but 2D videos are not capable of providing participants with realistic shoulder surfing experiences. Our qualitative data suggests that VR contributes to realistic shoulder surfing research despite being conducted in a research lab. And most importantly, VR studies provide researchers with an excellent opportunity to simulate real-world contexts that are otherwise challenging to study. For example, conducting shoulder surfing research on an ATM in the real world is almost impossible due to ethical and legal constraints. And with the help of such VR studies as we present in this work, researchers can actually enhance lab studies and provide participants with simulated real-world environments that eventually leads to more realistic shoulder surfing research. I would like to invite everyone to read more about our work in the paper, including the results from our interviews, the limitations of using VR for human-centered security research, and about 4 recommendations to support researchers when using VR for shoulder surfing research. Thanks a lot, and thanks to all my co-authors and to my academic friends and institutions. Thanks a lot.
Thank you, Florian, for that nice presentation. I want to remind all the audience to please put your questions on the Discord channel for the security session. We will go through the presentations one after the other. And at the end of the talk, of all the talks, we will then have a Q&A session with all the authors from the questions that we have collected from Discord. So without further ado, the next presentation is also by Florian Mathis on the paper titled, "Can I Borrow Your ATM? Using Virtual Reality for Simulated In Situ Authentication Research." Okay.
All right. Yeah. Thanks again, and thanks for tuning in to our IEEE VR paper presentation entitled, "Can I Borrow Your ATM? Using VR for Simulated In Situ Authentication Research." So let me tell you a bit about a story at the beginning. When we go back to 1967, this is how users withdraw cash on ATMs. As you can see here, ATMs were equipped with a keypad with digits from 0 to 9. Now, what is interesting here is that 55 years later, if we go to an ATM in Australia, in the US, in the UK, or in any other country, nothing really changed. There is still a keypad, and the way to authenticate is often still to enter a 4-digit PIN, which we know from existing research is not secure at all. There are actually some more secure authentication systems for such public displays. On the left side, for example, you can see QAuth, a system that makes use of media gestures and touch gestures. And on the right side, you can see an authentication system that makes use of eye-gaze interaction. Now, while these systems are highly usable and more secure than traditional 4-digit PIN authentication, their evaluation happened in a traditional lab setting, which means that it remains unclear how well results from corresponding user studies apply to a real setting. For example, when we take the work by Dampf et al. As an example, a key design concern of the study here was the recreation of the sights, sounds, and experiences that are typical of ATM machine usage in public. And in this work, we aim to enhance the evaluation of such novel authentication systems by immersing users into highly realistic authentication scenarios with the long-term goal to transition academic research artifacts into practice. This means that in our study, users' primary task is not to authenticate, but rather to withdraw cash, which is usually the case in the real world. In other words, people do not go to an ATM to enter a PIN. They go to an ATM to check the balance or to withdraw cash. But this is actually not how novel authentication systems are currently evaluated. Therefore, we first implemented two baselines which represent the scenario where a user's task is to authenticate only. This is basically state of the art how these systems are evaluated. And we did this in the real world and in VR to see how well results from VR transfer to the real world. We then evaluated the same authentication method in Situ, which means that the authentication was integrated into an ATM and participants had to go through an entire ATM interaction scenario while using our provided authentication method. We had an additional condition in VR where we placed virtual avatars next to the ATM to investigate the extent to which they impact the user's authentication behavior and performance. As an authentication method, we replicated a novel authentication method called color pin, which makes use of a traditional keyboard for usable and secure input. The idea here is that one digit is mapped to a character on a keyboard depending on the color. For example, if a user wants to enter the 1 in black, they would need to press the character U on the keyboard. And after one input, the characters are randomized, which means the mapping between a digit and a character changed due to security reasons. To enter the digit 2 in red, for example, a user would need to press the character K. We discussed the motivation of color pin and provide more details in the paper. From a technical perspective, we used a green screen and MetaQuest 2, a few tripods and a Logitech C920 to partially blend the real-world keyboard into VR and to enable participants to provide input on a physical keypad while being in VR. And based on this setup, we then aimed to understand how well a VR-based in situ evaluation compares to a real-world evaluation and actually impacts a real-world authentication system's usability results and the extent to which the use of VR contributes towards a sense of authentication realism, even in a controlled user study. We conducted a within-subject experiment with 20 participants here, and participants went through authentication scenarios where they had to input a 4-digit PIN in 2 different environments, in VR or in reality, and in 3 different contexts, which is basically the lab, the VR ATM, and the VR ATM in public with additional bystanders. And we measured several common usability measures, such as authentication time, error rate, and perceived workload. And we also used the IPQ questionnaire to get insights into participants' sense of presence and being part of such an ATM authentication scenario. First of all, there is no evidence of a significant difference between our different settings when it comes to the number of input corrections and input errors. However, our results confirm that input in VR takes longer than in the real world. And more importantly, we noticed an increase in authentication times from the lab to the ATM environments in both reality and VR. Authentications in the replicated real-world ATM scenario took 24.7% longer than in a traditional real-world lab setting, and the same pattern can be found in the VR conditions. In both the real and virtual environment, participants' sense of being part of an authentication scenario increased significantly from the lab to the ATM environment. There was no evidence that participants' perceived workload was significantly higher in one of the scenarios. And what is particularly interesting from a human factors and human-centered security lens here is that participants' feeling of being part of a user study was significantly lower in all ATM scenarios compared to our physical lab setting, which is the state-of-the-art evaluation approach. This means that embedding authentication systems into real scenarios contributes to participants' perceived realism. And it also shows that the use of VR to conduct simulated in-the-wild evaluations in the authentication domain achieved promising early results and can actually have a long-lasting impact on the human-centered security field. Because we noticed in our study that participants change their input behavior depending on the scenario. So just the fact that we introduced them to an ATM authentication scenario made them change their input behavior compared to the authentication in the lab setting. In summary, we combined here traditional user-centered security research with VR studies. We showed how VR enables and supports researchers to conduct simulated in situ real-world authentication research. But despite the high realism of our study environment using VR, we were still not able to elicit specific authentication behavior, such as pin shielding, which has been shown to be a thing in the real world. Our results suggest that the context in which usable security systems are evaluated impacts the usability research findings, and more importantly, it can change the way in which users interact with such systems. And even more important is that using VR as a research method complementary to traditional lab studies or field studies opens the door to move usability evaluations on real-world prototype systems out of traditional physical lab settings. And in the long run, I hope that this contributes to affordable and more realistic authentication research. Please read more in the paper about our results and our vision of establishing VR studies as a complementary research method for simulated real-world human-centered security research. Thanks a lot, and feel free to get in touch with me.
For those of you, thank you for that nice presentation, Florian. For those of you who are just joining us, please put your questions on Discord. We will address the questions towards the end of the session after all the presentations are completed. So we will move on to the next presentation. The next presentation is by Sean Banerjee, combining real-world constraints on user behavior with deep neural networks for virtual reality biometrics. Okay. Sean?
All right, thank you. So let's just jump headfirst into this. Bear with me 1 second. Okay. So as VR starts expanding into domains such as healthcare, education, finance, it is important to secure data. Now, traditional credentials such as usernames and passwords, once a malicious user has gotten a hold of this, game's over. They can get into your system, do anything that they want. And until you change those credentials, you're kind of in a lurch. So what has been emerging over the last few years is this idea of using a person's behavior in VR, so how they're interacting in VR, as a biometric signature. So some initial work back in 2019 from my group, which was published in Multimedia Modeling, looked at nearest neighbors. Work by Pfeiffer looked at using random forests. More recently, Florian's here, Florian's just presented, my group, Liebers, we've all started looking at deep learning approaches because they do provide a much better performance when we're starting to look at authentication and identification. But the moment we start using the word deep learning, there is a problem we got to think of. Traditionally, when we think of deep learning, we think big, large data sets. The largest data set right now for VR biometrics is a 511 user data set. But this data set actually does have ecological validity concerns because users were generally looking at a 360-degree video while standing still. And if we think of VR, that's not very plausible because people are going to be moving around in VR. They're going to be going from A to B, doing some tasks. So the larger sort of body experience data set that exists is from my group, and it is 41 subjects using 6 different VR systems from the HTC Vive, HTC Vive Cosmos, Oculus Quest. So you can see it's a kind of small data set. So the questions we started asking is, how do we address the idea of small data sets, deep learning? So one way to look at is to do this idea of data pre-processing. If you look at related work has taken a variety of approaches to do normalization of the input data. Mathis, in their work, to the best of our knowledge, did not do any reported normalization. Our previous normalization approach used a device level normalization, which I'll show a bit later. And that kind of erases the relationships that exist between VR devices, your headset, your hand controllers. Libras had an interactive phase where they normalized based on the height and arm length, but this requires this initial pre-phase where users are going to have to wait until the authentication system comes into play. So let's look at input data going into a VR system. We could pass the input data as recorded. Now this is all fine and dandy as long as the user was giving you data on one single day. But if the user comes in on a second day, they may be moving positionally in space. And the moment they start moving positionally in space, things don't kind of work too well for your deep learning algorithm. We could do a system centering, so center everything around the origin. We see that there is some vertical spread. Now, if we do system normalization, we notice that the vertical spread starts to go away, but the positional information in between our devices has not been addressed. We could do device level normalization. Now, what we start noticing is that even though all the devices are centered around the origin, the device-to-device information is now long gone. And if you think of our human body, our head is connected to our neck, it's connected to our shoulders, connected to our arms. So it's not like our body parts are just hanging arbitrarily in space. So what our work does is it looked at this idea of displacement vectors to represent device relationships. So we start with this individual device normalization. Then we add on to it the left-right distance, so the distance between the left controller and the right controller. We also add in the right controller and headset distance. And finally, we add in the left controller and headset distance. So adding to the device normalization, these three other features that hopefully will give us a better understanding of the person and hopefully help the deep neural network in the presence of sparse data. So the data set that we use is our 41 subject data set. This is data collected using 3 VR systems, 2 sessions per system. In the system, user picks up a ball, throws it at a target, 10 throws per session. To check to see if our approach works well, we tried 2 authentication approaches. One is our prior Siamese neural network, and one is the classifier approach from Mathis's work in 2020 in Kai. So we start looking at results. The results here are shown as A, indicating no processing, BC indicating the system centering, BN indicating the system normalization, C indicating device normalization, O indicating our proposed approach with the distance vectors. The labels on our histogram, the 1, the 5, the 10 is the grouping. So here we're breaking down the 41 users into groups of 1, 5, and 10. When we indicate test, we say that the query and the library are from the left out group of users, all indicating that the query is from the left out group and library is from all users. Now, looking at the Siamese neural network, we notice that our proposed approach gives the highest accuracy most often. This is a good thing in the presence of sparse data. Looking at the classifier, story is the same. Again, our approach has the highest accuracy more frequently. So we're showing that this, distance vectors associated with the devices is actually helping in the long run. So as we look to the future, there are things we should be considering. Large-scale data collection has to be done. There's a lot of us working in the domain of VR. We all need to start interacting together, talking to each other, getting this dense VR data set going. VR data sets have to be collected in a variety of environments. I'm really impressed with Florian with your ATM scenario. I'd love to get a copy of that so we can start collecting data on people using ATMs in a variety of VR scenarios. There's our ball throwing application. We've got a few other applications going on. Long-term use is a question that is unanswered. How do people feel as they use VR for hours and hours? The metaverse is coming. And we're going to be in there doing a lot of things. How does comfort play into a role? Finally, what about multi-step activities? The task we looked at, ball throwing, pick up, throw a ball, there's a start and an end. But everyday tasks have different pathways you can take to go from the start to the end. So all those things need to be looked at. And that is the end of my talk. Thank you.
Thank you for that nice presentation, Sean. So for those of you who are just joining us, please be sure to put your questions on Discord. We'll be collecting them and using those questions towards the end of the session during the Q&A. Let's move on to the next presentation. The next presentation is by Zhisheng, and the paper is titled HoloLogger, Keystroke Inference on Mixed Reality Head-Mounted Displays. Zhisheng?
Hey, hello everyone. Thank you for having me here to present our work. This is a joint work between George Mason University and Automatic Data Processing Incorporated. The mixed reality technology merges computer-generated digital objects with physical objects in real time. With the advancement of MR, diverse applications have been built into MR systems, including online payment, email, or social media. And to use these functions, sensitive information is also entered through the HMD, for example, credit card numbers, private communications, and account passwords. And in order to design a secure MR system and ultimately make MR a trustworthy technology, we need to first understand the potential vulnerability of sensitive MR data. And keystroke inference attack that infers user inputs by analyzing human-computer interaction is one of such potential security threats to MR. When users utilize the head movements or hand movements to interact with the MR system, their interaction gesture is exposed. And this type of attack has been conducted successfully by capturing user or device motion through different side channels, such as video recordings or wireless signals. However, these keystroke inference attacks require additional hardware, such as cameras or wireless transceivers, and the extra hardware must be installed near the users without alerting them, which limits the potential attack scenarios. And here we expose a more dangerous malware-based keystroke inference attack in MR, where motion information will be analyzed to infer the user input without requiring any extra hardware. And the MR system does not require any user permission for an app to access its motion data. Therefore, we can employ the malware on any benign app to record the headset motion for keystroke inference without alerting the user. And here's the threat model of the attack scenario. We assume that the user enters sensitive information inside private areas, and the malware is disguised as a benign app and installed in the user's device. And also the malware can detect the headset motion without the user permission, and the attacker knows the layout of the virtual keyboard. And realizing such an attack scheme is non-trivial. The first challenge we face is that there exists 6 degrees of freedom device motion in MR. In other words, both HMD orientation and location. Therefore, the virtual keyboard will not follow the user when the user steps away from the keyboard. And the same head orientation may point to different keystrokes. And also different head locations may result in the same keystroke. And the second challenge is that there is no explicit motion indicating the keystroke moments. A user makes keystrokes in MR by performing a finger tapping gesture with her hand in front of the HMD camera, known as the air tap. And this process does not incur any obvious device motion and thus leaves no indication of when a key is selected. And to tackle the above challenges, we develop these 2 modules. The first module, target key tracking, maps the 6 degrees of freedom HMD motion to the target keys on the MR keyboard. And the second module, keystroke inference, identifies the keystroke moments by exploring the unique timing pattern of the HMD motion during an air tap, and then it identifies the repetitive input of the same key. The first step of the first module is to derive the cursor position on the virtual keyboard. Based on the coordination of head orientation and location, the intersection point between the user's gaze direction and the virtual keyboard plane is derived as the cursor position. And then by comparing the cursor position with each key's boundary, the target keys can be identified. And then the first step of the second module is to recognize the keystroke moments based on the cursor speed. Since the user stabilizes the cursor to commit the keystroke, the segments with low cursor speed is first identified as a keystroke moment. And then to recognize repetitive keystrokes, first within each keystroke segment, the most frequently appeared key is set as the base candidate. Then the segment longer than others is recognized as a repetitive keystroke. The corresponding base candidate will be repeated twice in the inference result. And to improve the HoloLogger's performance, we conduct several steps to calibrate the above inference results. First, a modified repetitive keystroke is desired, since it is possible that when a user has trouble aiming at the target key and spends a long time stabilizing the cursor, the segment would be long, but actually it only includes one keystroke. So in this way, we remove the repetitive keystroke, then set other long segments as repetitive keystroke. And secondly, a revised base candidate may be necessary, since it is possible that a user is trying to commit a keystroke, but spends the same or even longer time looking at the nearby key than the key to strike. So we further divide the segment into different groups of samples aiming at different keys. And then the second most frequently aimed key is set as the base candidate. Then we validate the HoloLogger through several tests. We recruited 25 participants, each of them typed 30 passwords. The password length ranges from 4 to 8 lowercase letters. And here are the precision and the recall of the keystroke inference across all characters. We can see that the HoloLogger achieved promising performance inferring all the characters. And as shown here, the top 1, 3, and 5 accuracy of inferring passwords typed at the initial position 1.5 meters to the left and 1.5 meters to the right is around 73%, 89%, and 93%. This proves that the user movements does not affect the inference accuracy. And this is because the effectiveness of the HoloLogger's 6 degree of freedom motion data tracking. And here is the top 5 accuracy of inferring passwords with or without repetitive keystrokes. We can see that although the top 1 accuracy is low for password with repetitive keystrokes, the accuracy of cases with more attempts is only slightly impacted. This is because the inference calibration process effectively identifies most of the repetitive keystrokes within only 5 trials. And here is the conclusion of our work. We implement the first prototype of a malware-based keystroke inference attack towards HoloLens, and then we design an attack framework to infer keystrokes by analyzing the 6 degree of freedom head motion and the unique head navigation pattern during air taps. The HoloLogger prototype is evaluated through extensive evaluation and achieves top 1, 3, and 5 accuracy of 73%, 89%, and 93%. The exposure of this attack will alert MR users, inspire MR developers in designing more secure MR systems, and call for research to establish trustworthiness in MR systems. And that's all for our work. Thank you for listening.
Thank you for that nice talk, Zhisheng. So moving on to our next presentation. This will be again by Sean Banerjee. And the title of this paper is Temporal Effects in Motion Behaviors for Virtual Reality Biometrics. Sean?
All right, just like Groundhog's Day, we meet again. So, won't go over this. VR biometrics, kind of gonna need it as things start getting really serious in our future metaverse. So, while behavioral biometrics for VR has existed, we kind of have not answered a critical question, which is, well, what exactly happens as time passes? You know, we're all getting older, our bodies are changing, our bodies are evolving. I'll be honest, I lost about 30 pounds over the last 4 years. So I've looked at my behavior inside of VR. Using this ball throwing application, I throw differently. My muscle mass has changed. And existing research that exists has simply fail to answer this question. Now, if we kind of go to other behavior-based fields, for example, Gait has looked at the fact that clothing, shoes, all of these influence gait recognition. But clothing, shoes are not so critical in the domain of VR unless you're really wearing this bulky jacket or you're really wearing, for example, platform shoes, if you're gonna do your best, reincarnation of the band Kiss. But in the world of keystrokes and swipes, we've started seeing that this idea of habituation, so how people learn, plays a big role. So some of my past work in that domain shows that early data, when user behavior is very, very variable, is not very good for creating authentication identification systems, while later data becomes better and better until the user behavior once again changes. So we said, can we actually study this in 3 different timescales? And we got lucky because we actually have data for this. We have 2 studies using our ball throwing application where a user picks up a ball, throws it at a target. And we've collected this data on the HTC Vive in our Ajit study where the data was separated by just a few days. Then we did a longer study where we got data from the Oculus Quest, the HTC Vive, and the HTC Vive Cosmos. Now, in that data, again, we have short time scales, some longer time scales, but also we have this big time scale between our second Vive session, this Ajit study, and our first Quest session, which range from anywhere from 6 months to a year. So taking our original idea of using Siamese neural networks as our biometric authentication scheme, we said, how is authentication influenced in short, medium, and long timescales? So for short timescales, we said user comes in on day 1, does this ball throwing action. User comes in on day 2, does this ball throwing action. Do the entries on day 2, do their positions in time match better to some entries from day 1 and their position in time? Now we're only comparing day 2 trajectories to day 1 trajectories and keeping this temporal behavior the same. So we're never going to, train on something that came in the future and test on something that came in the past. We looked at data from Quest 1 to Quest 2, exactly 1 day apart for 36 users, Vive 1 to Vive 2, 18 users, Cosmos 1 to Cosmos 2, 24 users. And what we observe is that we don't see any major trends. If we look at these bar plots, these are all queries 0 to 9, so 10 queries from day 2 compared to day 1. And we don't see that, later queries on day 2 are matching better than later queries on day 1. So this says that the short time scale, because VR is so immersive, it may be that users don't have to go through this habituation phase. The next time scale we looked at is medium time scales. We said less than 10 days, more than 10 days. Here, L and Q start for library and query. Q, C, and V are Quest, Vive, and Cosmos. The 1 represents session 1 of data, 2 represents session 2 of data. Now, if you're paying attention, you'll automatically see, hey, you're greater than 10 days, it seems to be working better. That's kind of counterintuitive. It seems like the further people go away from the system, the better they're doing. That's not the case. It's just that our authentication algorithm does poorly on some subsets of users. And in the bottom, we show the median results. And we see that the median, aside from a few outlier users, is pretty uniform. So at the medium time scale, given the limited data that we have, we can say that perhaps there is no major effect. Finally, as I said, we also can study this long time scale behavior. And this long time scale behavior looks at user evolution over these 4 windows for the HTC Vive. We look at user 16 here on the right-hand side. We look at the right controller. User 16 actually went from an underhanded to an overhanded throw. We look at user 1. Their left controller behavior has changed from the Vive 1 and Vive 2, which was from our Ajit study, and Vive 1 and 2 from our Miller study. So we said, how does this temporal change actually affect our neural networks? So we trained 3 types of networks. In network A, we trained on the VA1, VA2, and we tested on VA1, V1, and VA1, V2. So really, the testing is in a much wider time scale. And we do terribly. This is kind of expected because the time scale is so vast. Then we said, what if we sort of straddle that time scale? What if we train with VA1, V1, and then test with VA1, V1, VA1, V2? We do better because now we're learning this temporal difference. Finally, we said, what if we pick a best of both worlds network where we have the best of network A and the best of network B, and we create this network C? We do even better. So in the long time scale, we're suggesting that training neural networks that can learn this temporal difference is going to help us. Now, in terms of future work, and as I said in my prior talk, there is a lot of work to do. We have to have a large scale longitudinal data set, and we have to involve our local schools, our local communities. We have to have tasks that have both physical and cognitive changes. We have to look at people's familiarity with systems. We've got to investigate how behavior changes based on increasing and decreasing cognitive loads in the VR task itself. We've also got to start looking at the role of transient behavior changes. For example, a person gets a phone call or a person gets called away. Now, in my smartphone study, we used to see these funny behavior changes when we were collecting data in the lab, is if you started talking to your participant, their entry systems would completely change because they were being distracted. So future work, we've got to have this large scale, multi-system, longitudinal data set in order for us to even make the guesses on what temporal changes do for VR biometrics. And that's my talk. Thank you, folks.
Thank you for that nice talk, Sean. So our last presentation for this session is by ülkü Meteriz-Yildiran. The title of the talk is A Keylogging Inference Attack on Air Tapping Keyboards in Virtual Environments. ülkü?
Thank you very much for the introduction. Hello, everyone. My name is ülkü Meteriz-Yildiran, and I am thrilled to present our work, A Keylogging Inference Attack on Air Tapping Keyboards in Virtual Environments. So the features offered within the AR head-mounted displays allow diverse use cases, including simulation, training, entertainment, and assistance. To support such diverse use cases, these technologies offer new interaction methods with the virtual environment. To fully integrate AR technologies to our daily lives, the research community is working on more natural interaction methods for more convincing perception. The methods include, but not limited to, voice commands, hand gestures, hand and gaze tracking. So in this work, we take a closer look into the privacy impact of input entry methods facilitated by hand tracking. So in our system model, we consider a victim user wearing an AR HMD capable of hand tracking, and the user types on an AR keyboard that is only visible through the AR glasses. And the adversary tries to recover what the user has been typing on the private virtual environment. So in our threat model, we consider 3 scenarios. For all scenarios, the adversary obtains the same data, but the data collection medium changes. So our attack pipeline consists of 5 steps: deep key tap localization, key tap localization refinement, candidate key center generation, candidate keyboard reconstruction, and best worst ordering. So in the first step, we leverage the fact that the hands follow certain patterns while typing on the AR keyboard, which makes key tap gesture distinguishable. Based on this observation, we localize the key tap specific patterns on the data stream. The coordinate system of the low-level data changes as the hand tracking sensor is placed in different positions. Therefore, we first pre-process the data, and then we perform temporal localization on the data stream using multi-head CNN. In the second step, we refine the localized key tap positions. We know that the key tap points lay on a plane in 3D. Therefore, we estimate the keyboard plane for the candidate locations from the first step. Then, by following the hand traces, we refine and reduce the dimension of the key tap points on the estimated plane. So when each key center on the AR keyboard is treated as a cluster centroid, each key tap point should belong to the cluster of the associated key. Based on this observation, we argue that proper clustering of the found key tap points partitions them into associated key clusters. For such proper clustering, the ideal thing would be knowing the number of unique keys in a typing session. However, this is not the case in our system model. To address this issue, we apply agglomerative hierarchical clustering on the key tap points and generate a set of clusterings with varying number of clusters. The cluster centroids are treated as candidate key centers. So in the fourth step, we find candidate keyboard reconstructions using the candidate key centers. To achieve this task, we account for the possibility where each candidate key center may correspond to any key on the keyboard model. At each session, the coordinate systems of the hand tracker and adversary's AR keyboard model changes. And there exists a similarity transform between these coordinate systems. Once we found this transformation, we project the key tap points on the adversary's keyboard model. As a result, we map the key tap points to their corresponding keys on the AR keyboard model. So in the previous step, we obtained countless inferences as an output of the exhaustive process. Many of those inferences are inaccurate due to incorrect pairings. Although the search space is significantly reduced, it is still infeasible for an adversary to consider all reconstructions. However, accurate reconstructions have certain characteristics which we measure with inference measurements. In this step, we filter out the inaccurate keyboard reconstructions and order them from best to worst using the inference measurements. So to evaluate the performance truly, we conducted experiments assessing the performance of individual steps as well as the end-to-end pipeline. The experiments involved 5 participants. The accuracy of the attack is measured with normalized navigational similarity and its HOP and top key variations. Keystroke detection stage of our pipeline includes the first 2 steps, deep key tap localization and key tap localization refinement. For the evaluation of deep key tap localization, we trained our multi-head CNN as a binary classifier. Then we performed predictions on the testing split. The prediction procedure takes the set of input segments and output found key tap events with their confidence scores. Given each ground truth key tap segment, we associate the found key tap events with ground truth segments, which are closest in time. We also keep track of the intersection over union of each association. We eliminate the associations with IEEE values less than the given threshold. The precision recall curves for left and right hands here show the results with varying thresholds. As we expected, a small threshold yields a better classification model. So the bar charts here show that with key tap localization refinements, we significantly decrease the number of false positives by slightly affecting the true positives. So let's move on to the evaluation of key identification stage, which includes the last 3 steps of the pipeline. For this set of evaluations, we collected 4 types of data from 3 participants other than the training data participants. The plots here shows the accuracy results we obtained with different HOP and top K variances. Within the first 500 reconstructions for email and R5 datasets, our key identification were able to reach 100% pinpoint accuracy. Similarly, we were able to reach 100% accuracy within the first 500 reconstructions for R10 and R15. Lastly, we evaluated the end-to-end pipeline. This table shows our results for all datasets and varying HOP and top K configurations. As the number of reconstructions increases, the accuracy also increases. So the maximum pinpoint accuracy achieved over all reconstructions is 68% for email, 76% for R5, 87% for R10, and 62% for R15. As we can see here in the green columns, we are able to list those most accurate reconstructions within the top 500 reconstructions. This figure shows a sample inference from the email datasets. As we can see, our attack was able to recover most of the sentences. As a countermeasure, we propose and analyze dynamic positioning. For X and Y dimensions, we define a translation vector T. After each keystroke, we form a translation vector by randomly choosing the angle and the length. Then we simply slightly move the keyboard in the virtual environment. With this method, we protect against the key identification stage of the attack. Thank you for your kind attention. You can find more details on our methodology, evaluations, and countermeasures in the paper. For your questions, please do not hesitate to contact me in the listed email.
Thank you, ülkü. And I thank all the speakers in this session for their nice presentation. So now we move on to the Q&A session. Please, audience, if you have any questions, please put them in the Discord channel, and we will fetch them for the Q&A session. We have about 12 minutes for Q&A remaining. So I'll jump right in. So this first question is from Mason Manetta, and he asks for Sean Banerjee. with regards to one of your papers combining real-world constraints. Do you foresee any limitations or problems for applying your normalization method to data sets with motion data with different VR headsets and tracking systems?
Thank you for the question. I'll actually tag on Lauren and Mason's question together because they're both very related. So if you look through our paper, we actually did this on 3 VR systems. We did the HTC Vive Cosmos, and Oculus Quest, and we did go across devices. So we did Quest to Cosmos, Quest to Vive, Cosmos to Vive. So we've compared it all. And yeah, it works very good actually. But you know, again, small data set. As I kept saying, we've got to grow this data set to really, you know, hone in on the new devices that are soon to emerge on the market. You know, there's the HTC Focus that's in the market. There's now the Quest 2. So yeah, I think it'll work on anything, and we've shown it on 3 different systems already.
Okay, thank you, Sean. So this next question is for Shiqing, and this is a question regarding the HoloLogger paper. And so Brendan David John asks, he mentions, great talk, thanks. I have 2 questions. It seems the current module used is based on head pointing, not hand-eye pointing. Does the module extend directly when hand or gaze is used to select which character is being used? I'll ask this one by one.
Yeah, I mean, yeah, that's thank you for your question. Actually, I believe it can be directly extended since as long as it's using aiming modality, then it can be extended. Yeah.
Okay. And he further asks, do you hypothesize that a gaze-based entry system, which might be harder to attack and identify as a specific character, would offer more security against this type of attack?
Yeah, I believe it will be harder because I mean, because the user's head movement is kind of slow, but the users can move their eyes very quick. So it will be harder for the malware to track the user's eye movements. But as long as the system grants like a default permission to the app, I think it should be still considered as a serious threat.
Okay, thank you, Shiqing. So this is a question from the audience. This is for you, Sean, with regards to your research. This is again from Brendan David John. Excellent research. Thanks for your talk. In the spirit of some of the papers in the session, I'm curious if you have thought about attacks on your features for behavioral metrics. It's a good question.
So great question. Kholgade and I think Florian, I think your work also looked at, you know, what happens if you show a person a video of the VR session. So positional information, sure, you know, that's a dangerous threat. But orientation, if you look at our Ajit et al. Paper from AI VR, if I remember, that was the venue, we showed orientation is actually a much better feature, because I'm going to lift up my phone, see the subtle orientation change of my wrist. An attacker is going to have a real hard time mimicking that. They might be able to get the positional information quite decently, but orientation actually becomes a very good feature over there. Now, again, as I've been talking about data collection, you know, really, we need to get actors in the mix, you know, trained professional actors. We have a school of drama over here, so we're working with actors who are able to mimic human users better. So we're starting to collect some of this initial data set, and hopefully by next year, I'll actually have some of these really crisp attack data sets where we're getting the trained pros to be mimicking the human users to see how well do these features actually stand up in the long run.
Thank you, Sean. So now I want to give Florian a chance to address the question. So Florian, with regards to your work, one question that I have as a session chair who studies human factors in various VR systems is, have you considered, for instance, other privacy security aspects in the authentication process as user research that can be done using VR platforms as test beds in the authentication process? And what other interesting human factors research questions might you be able to study in the authentication process besides for instance, shoulder surfing?
Yeah, so in our recent works, we focus more on human behavior with, without not really looking at the attacker's perspective, more on how would users behave when they provide input. And we actually implemented a set of different authentication systems that are intended to be used in the real world in VR to see how people behave, and also how do they think in terms of social acceptability are these systems. So we basically try to really use VR as a test bed, as a platform there. And the first study, the VR observations one, that was focusing more on shoulder surfing as a threat model, which is actually the threat model I look into most. And then we more or less focus on the usability aspects, as I just mentioned.
Okay, thank you, Florian. Now I want to ask a question to, let's see, to ülkü. With regards to your key logging inference system, can the accuracy of the key tapping inference be affected by, say, hand tracking accuracy, latency, frame rate, the characteristics of tracking, for instance, from these in these VR systems?
Yes, of course. So actually, this is one of the points we discuss in the paper. For example, in the paper, we are using Magic Leap 1 as the target AR glass. And we observed that the hand tracking is not as accurate as Leap Motion Controller, which is a small sensor that's specific to hand tracking. So this is why we are using actually Leap Motion Controller in our study. Since the quality and the precision of the hand tracking is very important in this temporal localization problem I mentioned in the step 1, this is indeed a big step. And as far as I know, the AR glasses, upcoming AR glasses, is more cautious about this hand tracking presence, like precisions. So we are hopeful to see more quality in the hand trackers embedded in the AR glasses.
Okay, thank you, ülkü. Now I have another human factors question as I was looking at your research that I wanted to ask, and I'll just open this up to everyone. Anyone can chime in, and I want to remind everyone that we have just 3 minutes or so remaining in this session. So are there other aspects, again, this is a human factors relevant question, are there other aspects of human behavior that can be used to track for authentication, such as gait or motion relevant data? And do we need to consider, for instance, the capabilities of the user? What about users who have disabilities, for example, motion relevant disabilities? And would that would, of course, constrain their ability to do, key tapping or what have you. In that case, I think we need to be considering other modalities of authentication, don't we?
Yes, of course. Yeah, this is another direction to pursue maybe with this, but our observation is basically people tend to use their index fingers. So this is one of the common thing we observe in terms of human interaction with the system. So yeah, as you said, it can also be considered like the people with disabilities, how they interact with this interface, but this would be actually another usability study maybe. Yeah, we can extend the study with that.
Thank you, ülkü. Sean,
Sure.
Looks like you had a comment.
Yes, I was going to say, as we see something like Neuralink emerging, and I think I'll just, kind of answer Florian's question. Where is the future? Still going to be restricted with, gait has been very well studied in this domain. We've studied keystrokes, we've studied gestures. So I think it's going to be a lot of free-form interaction. VR systems do need to start incorporating more of the traditional sensors that we think of, fingerprint, iris, face, even face in very highly constrained scenarios. I also think that we're actually going to go backwards into the past a little bit. For some of you folks, that are students, you may not remember a bit of the prior history. Schnee-Grass many years ago, when they were looking at Google Glass, they looked at bone conduction. There was also the idea of, head movement to music. So we're going to see this going backwards into the past as we get more and more away from this tethered to our hands and bodies. And then, I'm really thinking, think sci-fi futuristic as we get the neural link interfaces. Now we're actually going to look at, more of the EEG, the brain signals coming back into the forefront. So I think for those of you that are students, this is a really exciting area to be working in. I mean, great papers so far. And anyone that has questions, happy to answer them offline as well.
Okay, thank you for that answer. And with that, let's close this session. We're now out of time. Thank you, everyone. Thanks to all the speakers for their very engaging talk. And thanks for all your discussion and input. Thanks to the audience for attending this talk as well. And we hope you will enjoy the rest of the conference. Thank you.